Shall we start the discussion?
Yeah, I'm all set.
Yeah, let's go.
Okay, great. So last time we had stopped just before the random forest section, so we can start from there. Let me just share my screen. Just 1 second. Let me know if you can see
Yes.
the book. Perfect. Okay. So I haven't skipped anything, just the text that says random forest at the bottom. So basically, a random forest is an ensemble of decision trees. So last time we spoke in length about, or discussed in length about the bagging and pasting methods and how they're different and so forth. So essentially a random forest is just a bunch of decision trees that have been brought together by the bagging method or the pasting method. But there happens to be a subtle difference between just bagging a bunch of decision trees versus a random forest. And that is that while growing the random forest, you introduce some extra randomness. So instead of using all the features as you would for splitting nodes in each of the decision trees, you first select a subset of the features for each tree, and then you're basically going to be splitting only based on those features. So this introduces more randomness, and this kind of introduces a tendency for the random forest to be less overfitting compared to just a single decision tree. So if you look at this sentence right here, instead of searching for the very best feature when splitting for a node that is across all features, it searches for the best feature amongst a random subset of features. So this introduces the greater tree diversity and trades higher bias for lower variance. And overall, this yields a better model. Is there any points to discuss here or any thoughts? I know we had some extended discussions on bagging and pasting, especially when it came to variance and bias. So I'm just curious if anyone has any thoughts or if this is blatantly obvious and we can.
Yeah, I think you've given a good description of how the random forest adds randomness by two ways. One is by selecting subsamples of the data for each tree, and secondly by selecting subsamples of features to split on for each tree. But I think the second one, my understanding of it is a little different than what you said, and I admit I can be wrong. But my understanding is that you select a given subset of features that you specify when you call the random forest classifier, and so you could tell it whether you want to select a given number of features, or you can tell it whether you want to select a given fraction of features, or you can tell it whether you want it to subtract to use like the square root of the number of features, which is what Leo Bremen, who invented the random forest, suggested. But I think from there, that feature set which you tell it, if you tell it you want, like say you want to use 50% of the features for splitting, then for every split in every tree, it's going to choose a different subset of 50% of the features. So not only for the trees, in other words, what my understanding is, it doesn't choose a subset of the features to use for each tree, a different subset of the features to use for each tree, but a different subset of the features to use at each split in each tree.
I see. So
if that makes sense.
So I may have misspoken. So that certainly makes more sense. So I do apologize for that. So the way that I
no need
was
to apologize, and I'm not even sure if that's correct. So I ask everyone, is that your understanding too?
He says that in the very next paragraph that Sarem has already highlighted. When you're growing a tree, read the para right after extra trees, and it's exactly what Joseph says.
It's hard to tell in advance, or you mean this? Or
No. When you're
Under
growing
extra
a tree in a
trees.
random forest,
Okay.
at each node, only a random subset of the features is considered for splitting.
Right. So I think so where I perhaps misspoke was saying that it chooses a random subset of features for each tree, whereas that is not the case. It just chooses a random subset of features to split for each tree. Is that a better way to phrase it?
No, actually, it chooses a random subset of features every time it makes a split. So in a tree, it will choose a random subset of features, then make the first split. Then it will choose another random subset of features to make the second split, and so on. Every time choosing a different random subset of features.
Okay.
Does that make sense?
So if I was so let's so I actually have a link open here that might be sort of useful. So let me share that as well. Just 1 second. Are you guys able to see
Yes.
the screen now? So I just sort of saved a few links that might be useful for the discussion. So essentially, according to this link, we see that the Bootstrap sample is sort of the bagging aspect of it, where we select a random sample of the training set, right? And then we build a decision tree by on this sample by picking the best feature according to a criteria. So split as you would for a decision tree, repeat until the sample is exhausted. And then, so this part is sort of like how many instances or a certain depth is reached. That's sort of the terminating criteria for building the tree. But then I think this is the line that we kind of are interested in. For each split, we first randomly pick M features from the D original ones, and then search for the next best split among the subset.
Yep.
So essentially, the total number of features, they're equal to D, and you are choosing M features for a split, a random set of M features, and then you're going to split on those M features, find the best split on those, and then you're going to repeat this process on the said M features until you sort of reach the terminating criteria. Is that a correct way to?
Yes. So during the building of a tree, you're using many different subsets of different random feature subsets.
Yeah, I think it also makes the split faster, right? If you recall the card algorithm, like by only choosing a subset of features to consider for splitting, then it just makes the splitting faster.
Yes.
And also it avoids the greedy, like always splitting in the same way because of that, because of the greedy nature of the algorithm. So.
Well,
Cool.
it's still going to be greedy, but it's just going to only use that subset of features to be greedy on.
So that's where the diversity and sort of randomness comes from, and thereby you sort of have a lower variance on the ensemble.
Right. I was saying basically, I mean, because it's greedy, and if you consider all the features all the time, and it would just be split pretty much the same way every tree.
That is true. That is true. That makes sense. Shall we proceed? Any
Sure.
other thoughts here?
So in the example, though, he sets max features equal to auto, right? Which basically is saying all the features.
Auto means square root 2, I think in this
No, I
case.
think square root 2 is by itself a parameter. There's log 2, square root 2. Auto, I think, is all features.
We could quickly check that out. So let's see. It doesn't matter if it's a classifier or regressor. Let's just look at
I
what
think,
was the parameter.
square root of n features, right?
Auto square root of number of features.
Right.
So that tends to agree with this particular judgment that for classification problems, you select square root of number of features. And then for regression, you take number of features over 3, apparently. Okay, so we can proceed further if no one else has any other comments or thoughts. So the extra trees or extremely randomized trees are an extension of the random forest idea, where instead of just splitting on a random subset of features, you also sort of choose random thresholds on which you do the split. So this makes it even faster than the random forest. And also in the process, by choosing random thresholds, you are sort of trading sort of more bias for lower variance. And because you're just choosing random thresholds and not trying to find the best threshold for each split, you can basically make this train a lot faster. And this was kind of useful in that if you're not sure whether to use a random forest or an extra trees, try both, which seems pretty obvious, but oftentimes we might not think of it and then see which one works on better on your cross validation.
Right. So this mechanism is another way of regularizing. And just to be clear, what you said is that we're going to get higher bias but lower variance when we do this, right?
Yes.
That's what you said, right?
Yes, that is correct.
Sorry, where did you see the random threshold?
So if you see, it is possible to make trees even more random by using random thresholds for each feature rather than searching for the best possible threshold.
Oh, got it. But is it always the case?
For extra trees, it seems to be the case, right?
That's kind of the definition of extra trees.
For extra trees, okay.
Yeah. So that's sort of the differentiating criteria between extra trees and random forests. In that by doing the random threshold instead of sort of the best threshold, you gain two things. You get better lower variance, and secondly, it's faster to train.
So how do they select the feature to do the split on?
That
Do they
procedure is, I believe, it should be the same.
The same as in random forest.
It's exactly the same as a random forest. You choose this best. Sorry, go ahead. I think Joseph, you had something.
No, go ahead.
I was just going to say that it's exactly the same as a random forest in sort of choosing which features to split on. But then the thresholds that you split on are like random.
I mean, but the main purpose we do this is to save on compute, right? So if you're doing the same process, right? But it says that the most time-consuming task is to find out the split for each feature, find out the appropriate split. So if you're doing that thing anyway, so it doesn't give that benefit, right?
I'm sorry, I'm a little bit lost here. So
okay, so it says in the end of second paragraph of extra trees that finding the best possible threshold for each feature at every node is one of the most time-consuming tasks.
Correct.
Right. So if you are anyway using your compute to calculate the best possible threshold and then just randomly choosing a threshold.
No, you're not doing
does
that.
Not make sense, right?
You're not doing that.
The process of finding the best feature involves the process of finding the best threshold as well, right? Otherwise, how would you know that one feature is the best feature?
That's where the randomness comes from in an extra tree. You just randomly choose a threshold and a feature to split on, right?
So the feature is also random?
So I'm guessing that you would, so this is just my educated guess, but I would basically think that you'd compute the impurity or mean squared error based on random threshold of the subset of features and then choose whichever one gives you the lowest.
Okay.
As opposed to like finding the optimal threshold for every feature and then choosing the best from those. At least that's the way I have it in my head. Joseph or anyone else, is that a...
That makes sense to me based on the reading.
Yeah.
Okay, yeah, that makes sense.
Yeah, because you still have to choose which feature you want to split on, and for that you need to make some kind of a Gini calculation or an entropy calculation.
But yeah, exactly. So the threshold that you end up choosing is random. So
Yeah. So
that's
that
the
does save some time.
yeah, yeah. So if there's no things to discuss further here, we can go into feature importance. So feature importance is kind of super useful. And I think that this is an underrated quality as far as random forests go, and decision trees generally. Like when you can sort of quickly, when you have a problem where you have to do feature selection, it's quite nice to be able to just fit a random forest to your data and just get a sense of which features seem to matter, at least initially. And the random forest gives you a quick way of doing it. So the way that scikit-learn has it implemented is that at every node, when you build your forest, you are calculating sort of the impurity measure, like how homogeneous the nodes, the children of each node are after the split. So by sort of leveraging that information, you can basically take a weighted average, where like every node's weight is equal to the number of training samples that are associated with it, in the sense that the more the split, so let's just take a feature, right? Let's find all the nodes in the tree that use that feature to split on, and then let's see how much that feature reduced the impurity across all of those nodes, and then let's normalize this score across all of the features. That gives you sort of the feature importance. If that sounds a little vague, I do have sort of a let me just move this, sorry. So if you look at this example, so basically this is the iris data set, and you can see that the initial split is on the sepal length, and then the petal width and so forth. But when you need to compute the feature importance, so you're starting at the top. So the very first feature is the sepal length, right? So if you look here at this tree, the sepal length is used at the root, and it's also used at sort of this rightmost node, right? So what you do is you look at how much using that feature to do the split reduce the impurity. So you can see here that doing the calculation. So this is the score that you're probably very familiar with from the decision tree chapter, and you're computing the score at every node where this feature has been used. So this is the root. So if you go up here, you see it's used here, and then the second place it's used is here. So if we look at the two values, they sort of correspond to those. And then when you sum them up, so 0.20 plus this 0.0016, you can see that the total score for sepal length is sort of the sum. Sorry, not the sum. Over here. Sorry, the total sum is here. And then you compute this for every single feature. So sepal width, petal length, petal width. And then you have sort of the summation, and then you normalize it by this. So you take this and then divide it by this, take this and divide it by this, and so forth. And then you get a number, and that's your feature importance. And that's how scikit-learn is computing it for sort of a random forest. Is that clear?
So just to be clear, you say that when you say reducing the impurity, the Gini impurity, what we're talking about is it's making a sharp split between different classes. I mean, if all the classes were equally likely, that would be a very quote unquote impure situation. But if your feature splits and separates, lots of data into one class, and it separates data into different classes rather than having them randomly distributed among the classes,
right,
then that feature is reducing the impurity.
Yes. So the more homogeneous the samples are after the split, the better that feature is at sort of distinguishing across the samples that came to it. So if I'm splitting into two nodes, let's just say, let's just actually look at this, right? So I have 150 nodes. So this is the start. Sorry, I have 150 nodes here, right? 89 plus 61 seems about right. So after the split, I have 61 nodes from the first class and sort of 59 nodes here, right, after the split. So basically, if I look at how many samples there are for different classes, it's actually mostly sample A in this split and sample B in this split. So essentially, this feature for this particular node has done a really good job of doing this splitting or classification. Similarly, if I look here for sort of where was the...
I think if you look at below node 2 that you were pointing at, that shows exactly how the entropy drops to 0.
Right. Basically, when you have all the samples that are only from this particular class. So in this case, sample B is the only sample that's left at this particular node. So there's no sample A. So that's entropy 0. So it's pure. So essentially, you're seeing how much it's reducing impurity at every split. And the more that a feature is able to do this across all the nodes in which it is involved, the more important it is in the model. That's kind of the way to think about it. And then what you're doing is so that you have all of these values normalized to, say, they sum up to 1, you sort of divide it by the total score so that it normalizes by 1. So that's kind of what's going on here. So this sigma right here is basically summing all of this, and then this feature importance for the sepal length would be this over this, right? So if we sum all of this, you should get 1. Does that clarify?
So do you calculate at the bottom, or try to calculate Gini impurity for every feature at every
feature? So if you look at the sepal length, it's involved, like I was saying before, it's involved in 2 nodes in this example. So it's involved, the sepal length is a feature on which the split happens at the root, and it's also involved here. You see that it's not involved anywhere else.
Oh, so it's at every, wherever
that is the feature that's used to make this split.
Okay. So
you compute the reduction in impurity or the mean squared error, depending on the metric. I'm guessing they compute impurity anyway. So essentially what's going on is once you do that, you sum these values up. So it was involved in 2 places. So if I sum this up with this, I get this, right?
Oh, okay.
And then I rinse and repeat for every feature I used. And then I sum along this to get this. And then I take, for every feature, I take this, and then I divide by the total so that the feature importance is normalized to 1. So the maximum, like the sum of all feature importances for a particular tree would be 1.
And it says here it's averaged across all the trees?
Correct. That's what this table is doing. Okay. So in this case, he has 3 trees, and you are seeing how sort of the average feature. So this is the 3 trees. If I take this and divide it by 3, I would get this. That is basically, I'm summing across, right, for every feature. So perhaps this would be a good example. So if I took 0.07, 0.84, 0.16, I summed it and divided it by 3, then I basically get 0.36, right?
Got it.
Right.
Okay.
So that's it's a multi-level process of averaging.
So hypothetically, since it's a random forest, you could miss a feature?
Yes, and that's why you see that for one tree, this feature wasn't even used. So the feature importance is 0. And for example, the sepal length wasn't used in the 2nd and 3rd trees at all. So that's how it sort of averages out. Is that kind of clear?
Yeah, very clear.
And now that we understand how Gini importance, or actually you could also calculate entropy-based importance the same way, instead of using the Gini formula, you'd use the entropy formula. It turns out that for random forests, that there's a better method of computing importances that is less biased than the Gini importance than the Gini importances. And this is called permutation importance. And scikit-learn has a way of doing that. Permutation importance is interesting because it can be computed not only for random forest models, but for any other models as well. And so that even if you're not using, see, one of the advantages of random forest has always been that it has a way of calculating feature importances. But this, the permutation importance allows you to calculate feature importances for any model, even if it's not a tree-based model. So, you know, a neural network model or any kind of other model. And the way it works is even easier than Gini importance. So what you do to calculate the importance of a feature is you take that feature, the column of values associated with that feature, and you just scramble them up. You just permute them randomly, and then you run the model with those random values. And you see how badly it affects the accuracy, the resulting accuracy. And if it has only a little effect on the accuracy, then you can conclude that that feature was unimportant to the model. And if it has a large effect on the accuracy, so that the accuracy goes way down when you when you scramble up one of the features, then you conclude that that feature is very important to the model. And so that's called permutation importance. It's much easier to understand than Gini importance, and it's also a better measure of importance, because Gini importance is subject to bias when you are overfitting.
So actually, I have the permutation importance open here. So this article is actually covering that as well. So that is a great explanation, Joe. Here's sort of, I mean, if you want to sort of use this example table right here to sort of walk through what's going on. So, sorry?
Is that also widely used as feature importance?
Yes.
Yeah, Gini has a problem when you have high cardinality variables. So if you use the Gini importance, that is the problem. If you have a variable which has, let's say, a lot of classes in it, then it's going to get biased towards that. So that's why you'd not want to use it in those scenarios. And there's also another complaint about like how it kind of does well on your training set, but doesn't really do well on your test set, which I don't understand very well. But that is another problem that you have with the MDI importance, where permutation importance does not suffer with those two problems.
Yeah, that's the overfitting problem, the last one you mentioned, Gautam.
So this paragraph actually sort of summarizes what Joseph was explaining. Basically, the rationale for calculating permutation importance is the following. By randomly permuting the predictor variable x of j, its original association with the response y is broken, y being the target. When the permuted variable, together with all the other non-permuted variables, is used for the out-of-bag observations, the prediction accuracy decreases substantially if the original xj was associated with response. So if x of j is a very important feature, like Joseph mentioned, if you scramble it just that one feature and you keep every other feature the same, you will see naturally that the accuracy or sort of the mean squared error or whatever it is you're trying to do or measure is going to deteriorate substantially, and therefore that feature is important. That's sort of the idea behind how you use permutation importance. Is that a explanation that sort of covered your talking points?
Yeah.
Okay.
And I have a quick question. So is it like attached to some sort of cost function or error? It's just like the tree-based methods?
Doesn't seem like it. I think that's one of the advantages of the permutation importance that Joseph mentioned, is that it's not just attached to, say, a decision tree or a random forest, because those split based on the impurity measures, right? Whereas permutation importance is applicable by the looks of it to any feature that you want to use in a supervised task. So if you have all of these features, all you're doing is scrambling the signal, and you're seeing how much the scrambled signal is affecting the performance. And the metric by which you are measuring it is here, I guess.
Yeah, I think mathematically the permutation importance is just the fractional reduction in the score. So if the score, if the score, if the accuracy score is reduced by a large amount, then the fractional effect on the score is large, and therefore the importance is large. So mathematically, how you calculate the importance, it's the fractional reduction in the score when you scramble that feature.
So we can see that here in this equation, right? So essentially, this is the original score, the term on the left. On the right-hand side of the equation, the very first term is if you didn't scramble anything and you just computed accuracy, or whatever the measure was, this is sort of the score. The second term is sort of after scrambling, what is the same score? And the delta between the two is telling you sort of the permutation importance score for that feature. And then you're going to normalize it across all the features, I guess.
Just to note that this all gives you only relative importance. They're not like a linear regression model where it will tell you what the exacting contributing factor is.
Can you repeat that a little bit? I didn't quite catch that.
Like for example, if you have like y is equal to mx plus b, and you know what m and b are, then you know exactly that is the contribution from x, right? M times x. Whereas in this case, it's just giving you a relative importance, like you mentioned, how you actually find what each of these values are, either in feature importance or in Gini. But at the end of the day, you normalize it. So it's only going to give you a relative importance. It doesn't tell you how much each feature actually like directly contributes towards your output.
I would think so, because at least for the Gini type of Gini based feature importance, you're not guaranteed that feature is going to be used in every single tree, right? So if you just use the raw values, then you're not really measuring the true contribution anyway. Right, because for example, if say a particular feature wasn't used in two trees, and you just said that 0.44 is its contribution across all three trees, that's wrong. Whereas like the raw score here, for example, petal length across the board is used in all three trees, and like if you sum that up, I mean, like how do you measure like how do you know which feature is important relative to another if it's not a level playing field? In the sense, if one feature was not used in two trees and another feature was used in all three trees, then that's not a fair comparison, right? So I don't see a way of the absolute score being possible for the decision tree feature importance. I don't know about permutation importance, but I'm curious to see if you guys have experience with that.
No, I think what you and Gal, I think it was Rekil, are saying is correct. That that for a linear regression model, you have an absolute, the coefficients give you an absolute measure of the importance of a feature. But for these tree-based models and for the permutation importance or for the Gini importance, it's only giving you a relative importance considered among all the features. Right. So yeah, what he said is I think correct.
Cool. Any other talking points on this? Otherwise, we can continue along. Okay. So anyway, so this is sort of what I started this section with, saying that random forests are very handy to get an idea of what features might actually matter. I preface might because without a clear understanding of the data, you can't really guarantee that this is always true. So the next section is boosting. And in boosting, it's basically an ensemble method where instead of like in sort of bagging and pasting and sort of the ensembles based on that, we spoke about how we can stack them in parallel and then train them in parallel. Boosting kind of takes the idea along a linear fashion, in the sense that you take a series of individual weak learners and you stack them one after the other, as opposed to making them learn in parallel. And the idea, there are two more sort of popularly used boosting methods, namely adaptive boosting or AdaBoost and gradient boosting. So in adaptive boosting or AdaBoost, essentially you are going to first train a model on your training set. You're going to see how your model is doing on that training set. And then you will find samples for which your model did poorly. And you take those samples, give them more importance. So you weight them higher and you sort of underweight the remaining samples on which the model did well. And then you set up another new model that's going to take this weighted training set and learn on it. And then you repeat this process over and over, either until you find you have exhausted the number of models you want to stack, or until you get a perfect prediction. So if you look at this particular diagram, initially you are starting with this set of training samples in the dark blue. You pass them through your model, and your model now produces a prediction, as you can see by the red line, but it's missed sort of a couple of the samples. In this case, it's just missed one sample. So I go back to my training set, I weight that one sample higher. The other samples are sort of weighted lower because my first model did well on them. I then take this new training set that's been weighted, rinse and repeat. And over the course of sort of doing this multiple times, eventually I find that I get a set of models that sort of compensate for each other's weaknesses. So that's kind of the idea between, that's sort of the idea of adaptive boosting. We can look through the equations that sort of give a much better idea than sort of this diagrammatic explanation. But is there anything to discuss before we jump into the math? Okay. So one thing that comes with a sequential model is that you cannot parallelize it, and therefore it's pretty slow. So if you were to compare sort of an ensemble of bagged classifiers versus sort of a boosted classifier, the boosted classifier, assuming you have the same number of weak learners for both, you would probably see that the bagged classifiers runs faster. And so let's look at the math. So basically, we start off with every training sample. So all of these blue dots being weighted equally, 1 over m. So the number of training samples are m. So we just give them an equal weight, 1 over m. And then once we sort of train our model, we then compute the weight for every we compute the weighted error rate for every predictor. So the way that it's done is you first, the numerator of this term is the sum of all the weights of the training instances where the model got it wrong, where the prediction was not equal to the ground truth. So you're going to sum all of those up, the sum of all of those weights. The denominator is just the sum of all of the weights of the training instances. So in a sense, you're sort of normalized the error that the model's made across all training instances. You've summed that up. And generally, if a predictor is more accurate, you will find that its weight will be higher. So naturally, so the predictor weight here, that's the next equation, is sort of this parameter eta times 1 minus rj divided by rj. So if we think about it for a second, if my predictor made sort of a perfect estimation, I'd have sort of r of j being 0, right? Because the numerator of the term would be 0, and this would be 0, meaning that the logarithm would be an enormous number. Whereas if my predictor was sort of making mistakes all the time, this would consequently be a very small number, meaning that this predictor is weighted very small. And what's very interesting is that if it made random guesses, like it's right half the time, then this would be 0.5, right? If this was 0.5, then you'd basically be getting a weight of 0. So that's what I think they mentioned here. The predictor's weight is computed using this equation where eta is the learning rate. The more accurate the predictor is, the higher its weight will be. if it is just guessing randomly, then its weight will be close to 0. So that kind of tells you how AdaBoost is accounting for each individual predictor's performance. And then the next thing that AdaBoost does is, we talked about how the training samples are reweighted before the next predictor has a shot at them. And this is how it's done. So the weight remains the same if the current predictor got it right. It's the weight times the exponential of the predictor score if it got it wrong. So this second term basically weights the samples that were misclassified higher than the samples that were classified correctly. And then you sort of normalize all of these weights once again by the sum of the weights. So that ensures that the scaling is sort of preserved. And then we then go through this entire process again, where we take a new predictor, pass all of these reweighted samples through it, and then we sort of compute the score, and we do this process over and over again. So the question then is, how do I sort of get the final prediction once I have my AdaBoost ensemble trained? So you basically take the maximum of sort of the, so you take the predictions from all the predictors, and then you get the weights from those predictors. And then the class that receives the highest predicted weight across all the predictors is the sort of prediction for that particular sample. So that's what this equation is saying. Any talking points here?
I have a question.
Sure.
So my understanding is AdaBoost is supposed to be used with the same type of predictor, the same type of estimator.
Correct.
Do you know if there's a way, or does anyone know if there's a way to mix the estimators? I know that we get the stacking later on, but specifically for AdaBoost.
So that's a tricky thing to think about, right? I mean, so if you just think about it from sort of intuition, if you have different types of predictors, they come with different types of errors and limitations, right? So they don't make the same mistakes. So what you are reweighting your samples on is the mistakes that your previous predictor made. So if you now took a different predictor that potentially does a different set of mistakes, right, and you are giving more weight to samples that it does well on anyway, then you see where we're going with this. It might not make sense. So AdaBoost on hybrid predictors doesn't seem to make sense, especially because it's reweighting the training samples after every iteration, right? Or anybody else have some thoughts?
No, I agree. I think you've expressed it very well.
But isn't that the purpose of the ensemble method, is to bring together predictors that make different types of errors?
Correct. But in this case, what's happening is, let's just say that this was a linear regression model. This was a support vector machine, and this is a decision tree or something like that, right? So I am going into this process with equally weighted training samples. So everything is fine. My linear regression makes some predictions here, and then I find that it's worked pretty badly for these two samples. Now I'm going to give these two samples a very high weight, right? And then I'm going to go here, and now my training samples are not set up in a way that's conducive for the support vector machine, because it might have sort of dealt with these samples well to begin with, but it might have had trouble with other samples that are weighted lower, right? So the point is that by sort of weighting the training samples based on the performance of another type of predictor, you are sort of messing up the situation where the next predictor does not make the same type of errors as the previous predictor. Boosting is basically trying to stack the same type of predictors where every sequential model corrects the mistakes of its predecessor. By sort of having every model belong to a different class altogether, we sort of mess that dynamic up. That's sort of what I was trying to express.
Okay.
Yeah, so Brian, this is an ensemble method, but it's restricted in the sense that the ensemble has to be of the same classifier. But there's nothing to prevent you from, at the end, from, you have your AdaBoost model, you can now ensemble it with a random forest model or with a linear regression model, and average those together. So there's nothing to prevent you from having different models at the end, at the last step.
Got it.
Right, and that's what stacking is all about, right? The section that we're going to come to in a second.
Yeah. Cool. Thanks.
Any other thoughts here?
Yeah, I had a question. Like, can you go back to the previous figure? I just wanted to know more about this learning rate parameter. What exactly is he trying to show with eta equal to 1, eta equal to 0.5? Like, it feels like eta equal to 0.5, lower the learning rate seems like better. I'm not able to understand what is he trying to depict with that.
So essentially, the learning rate is sort of telling, so if you look at this equation right here, the predictor's weight is sort of the learning rate times sort of its performance, right?
Right.
So a higher learning rate means that the predictor might be given a higher weight.
Right.
And let's just say that for whatever reason, so the way that I sort of understand it is that the learning rate is controlling sort of how the next set of samples are going to be weighted. So if my predictor, if I have a very high learning rate, but my predictor did very poorly, let's just say that the weights that I get here are still going to be somewhat high, right?
Right.
And then what happens is that is going to enforce that the next set of weights, the next set of instances where my next model is going to be trained on, those weights will be sort of inflated, which is what you want. Whereas if you have a very low learning rate and you sort of have very high performance, it's sort of tweaking how much the weights of the next layer are going to be, of the Ada boost is going to be sort of affected primarily. Does that make
the learning rate is kind of kept constant throughout, right?
It's a constant. It's a hyperparameter. It's constant.
So what you're saying is only just a scaling factor, right?
Yes.
So if you increase or decrease the learning rate, the weight that you are attributing to your misclassified stuff is in proportion same to eta.
Exactly.
It's linearly proportional, I think. Maybe not linearly. It's
but the kicker is that the eta goes into the exponential boosting equation before it gets before you normalize the weights.
Correct.
So it doesn't get normalized out as you might think. It affects the final normalized weights because of that exponential boosting factor.
Correct. So it's sort of a scaling factor on controlling how much you're going to weight the misclassified samples. At least that seems to be the intuitive way to think about it.
So is there something like, so which one would you prefer, like a higher eta, lower eta, given a scenario? Like practically what use case? I'm not able to kind of grab that part.
Eta tells you how much that you want to boost the weights of the badly classified examples, right? Because remember, you pass that eta into the exponential. So in that way, I like to think of it as a boosting factor, boosting parameter.
So how does that correspond with the figure there, then, Joseph? Like why
which figure?
the figure? If you go back,
this one or this one? 7.8.
Yeah, exactly.
Okay. Eta learning rate equals 1, learning rate equals 0.5. So it looks like the learning rate equals 1 gave a lot of weight to the misclassified examples to push the boundary, to push the boundary outward, right?
I thought it was first you find the boundary, right? And then you decide what is right and wrong, and then eta comes into play.
So what happens is if you basically weight certain samples more, the next classifier is going to do its level best to make sure that it doesn't mess up on those. So it might sort of try to, push the decision boundary around those samples just so that it gets them right. And in the process, it might create some more misclassification. So I think so the more aggressive the learning rate, you see that the boundaries are much more wonky for different classifiers. The smaller the learning rate, you see that it's okay making some mistakes, right? You see these blue squares on the other side, but you see that the decision boundaries are a lot more smoother because the misclassified samples were weighted less.
Right. Okay. But
right?
it kind of. Go ahead.
So let's say that my first classifier, right? My first classifier, let's say that this one. So in the diagram, if you can see this one right at the bottom, it made a ton of mistakes. So all of these samples are going to be weighted higher, and they're going to be scaled 1 times whatever the performance of the predictor was. Next one is done a little better because it knows that these are the ones that it has to focus on, and then you sort of increasingly do this to the point where eventually the fifth one is like, I'm not going to make any mistakes on these guys, right? Even though it means that I'm going to make a ton of mistakes on the other class, because you see the decision boundary just swells right across. Whereas if I have a lower running rate, you see that for each of the 5, they are getting better, but it's not like a sea change. You don't see this huge jump in the 5th one, right?
Right.
So
Kind of
that's
weirdly feels that as learning rate is increasing, it's kind of overfitting and trying.
correct.
Only the blue class, though, not the yellow class, right?
Yeah. And so it's showing you that, you know, the magic formula of increasing the weights on the misclassified examples has limits. You can't just keep doing that infinitely. You know, you won't get improvement if you keep doing that, because, you know, you'll run into the problem that, you know, that Sairam identified, that you're going to try to get perfect score on all the blue examples, but then you do that, but then you fall down on the yellow examples.
Yep.
But when you make that point, like, why is it that, I mean, no part of the algorithm says you need to weight only the blue, right? I would assume that they would be weighting the yellow too. Like, does that make sense, my question?
Yes, it does. But it also depends on so the percentage of yellow and blue samples that we have in the data set. Right. So let's just say that it's a skewed data set. I don't know if this is a skewed data set or not, but let's just say that there were more blue samples than yellow.
Okay.
Or my predictor got more yellow samples right compared to the blue samples.
I see where you're going. Okay.
Right.
Yeah.
Then the blue samples are going to be weighted more than the yellow samples. And consequently, every sequential predictor that follows is going to try to cover up that mistake.
But,
okay. Yeah.
You know, to answer Rekel's original question, it's kind of confusing. It seems like you'll have to play with it and do some CV, because the default, interestingly, the diagram seems to suggest that 0.5 would be better, but the default setting is 1.
Mm-hmm.
So if you actually applied the default, you get the diagram on the left.
Yes.
And so it seems from that, as to what Rekel originally started with, which is interesting, is how do I tweak it? It seems like you let it be default, but then you'll have to play with it if you actually want it better, because what you get as default is the left diagram, whereas as we just discussed, the right one is the better one in this case.
Right. And that's why it's a hyperparameter, right? It's not something set in stone.
But that's I mean, that kind of goes to what he was seeking, right? Like, how would you determine what it ought to be? And it seems like you can't just let the default operate in this case, because the default.
Yeah, I think you're right. You're absolutely right, Srinivas, because so the moral of the story is never trust the defaults. They work in they work in some cases, but they're not guaranteed to work in all cases. So the only sure way is to do cross-validation.
Yeah.
The main complaint with boosting that I have seen is that it's too much of tweaking, right? So that's why I was just wondering, like, is there something going on over here that we are missing with these diagrams? But anyway, I think, yeah, that makes sense. We can move on.
I mean, it seems like everything else is a function of the model's performance, right? So the only other thing I can think of is this particular snippet of code where what are you boosting? Are you boosting a decision tree or some other model? And that type of model might have some inherent characteristics that might contribute to sort of how much you need to tweak things and so forth. But it seems like the default AdaBoost approach is to have a decision stump. So a tree composed of a single node with 2 leaf nodes. That seems to be the default. But to answer your question, I think that would depend on what you are using as sort of the individual classifiers or regressors, depending on what you're doing.
So one more quick question. If you
Actually,
can go
this might answer your question. If your AdaBoost ensemble is overfitting the training set, you can try reducing the number of estimators or more strongly regularizing the base estimator.
I see. Can you go back to the previous page?
Sure.
The feature importance there for the MNIST data set, like, is this just showing, okay, the digit is in the center and nothing is there around? Is that what is kind of being portrayed in this?
So I think what it's saying is it's basically passed this entire 28 by 28 image into the random forest, right? And what it's done is it's basically going to say how important is each pixel for classifying that this digit belongs to this particular class. I can't really make out what number this is. This could either be a 0 or it could be an 8. I am not quite sure, but it seems like all it's doing is that apparently these pixels that are yellow and like white right at the center and maybe in some corner areas were very important in sort of classifying this digit. That's what it's trying to say.
Cool. Okay. Sounds good.
Which makes sense because most digits have pixels in the center. I mean, there are some that are missing, like I can think of 0 that's missing pixels in the center, but even that would help you to say whether it's a 0 if there are no pixels in the center. I mean, if there are low values of pixels in the center, then that gives you more evidence that it's a 0.
Right. That's a great way to put it. Yeah.
Everything at the center seemed lit up. So I was wondering, this shows more feature importance where the model is looking. It doesn't tell me if it's looking for a specific digit, if that makes sense.
So the other thing that you need to factor in here is that it's when you feed this into a random forest, you're going to vectorize it. So it's not going to be this 2D representation anymore. So the spatial context is lost.
Yeah.
Right.
But it does know the center. I mean, because the central, if you expand it into a,
So this would be a 784 times, 1 cross 784 feature vector.
Yeah.
And of those 784 entries, which of those are important? I mean, I guess when we come to convolutions and attention, this will become much more interesting because the heat map will actually make sense a lot more.
So there the heat map actually lights up a specific line, like if it's a 5 or a 0, that's what a specific line there that gets lit up. Here, the whole center seems to be lit up. That's why I didn't understand.
Any other thoughts before we sort of proceed?
Yeah, so I had a thought that I see that we're going to go into gradient boosting next, and that's a whole complicated subject by itself, and it's already 8:17. So I propose that we stop now and we go next week and do the next meeting and do the rest. And if we have time left over, we can actually start to talk about the exercises. So that means sticking in an extra meeting for chapter 7 and pushing the whole schedule forward by a few days, if that sounds reasonable to people. Because I really hate to skip, I really hate to give Sairam 13 minutes to go through all of gradient boosting. We just won't do justice to it. So if you don't mind, Sairam, taking up where we left off on this coming Sunday and doing a third session on chapter 7.
I would second that. Anyone else in favor?
Yeah, aye.
Yeah, that sounds good.
Yes, I think I can make that work. I just have to check my schedule.
Okay.
But I think I can make it
It's
work. And I
Sunday,
agree, it seems like too vast a topic to sort of just...
Yes. You can't do that in 12 minutes or 13 minutes.
So then I have one more question to squeeze in if you...
Yeah, in which case, Rakel, isn't it the case that sticking with the MNIST example, that it's actually the figure that he shows has been converted to pixels, because he talks about, is it really a 1 by 784 or is it back to a 28 by 28 heat
It's
map?
been reshaped back to a 28 by 28.
Yeah, reshaped after the model worked on it.
So we can actually verify that. So here is the, here is the data. You're fitting the data. So when you read it from scikit-learn, you're going to read it. See, it says MNIST 784. So that's going to be a feature vector.
But Saram, if you think of it in that way, it doesn't make any difference if it's 784 or 28 by 28, right? The model still, even though it's taking in a feature vector, it still knows how to distinguish between a 2 and a 3 and a 4 and a 5. It doesn't need the convolution.
was the reason I was starting there was to say then that it's, again, if it's doing feature importance and the permutation and all that, isn't it across all the classes? Therefore, saying that a pixel in the middle is the one that helps me the most in deciding
that's
amongst
exactly
all
what
the
it's-
classes, and then blah, blah,
Right.
blah, going across all of these set of pixels, and thereby coloring it and saying that the value of a pixel at location X, Y is the most helpful determinant in choosing across the 10 classes.
Yes, that's what I was
Right.
saying. That's why the central, because all the numbers have pixels. Most of the numbers have pixels that cross the center, although some of them have pixels that don't, that are not involved, like zeros. But then they're missing. Then they would have low values at the center. So the central pixels are the most indicative of which, are the most helpful in the classification. And of course, this model is a linear model. It just strings out the pixels in a row. So it has no idea of the spatial relationships among the pixels. It has nothing that is not folded into the model.
Yep.
So right, so it has nothing to do with a specific digit. It's just whether a pixel is involved in making a prediction or not making a prediction.
Yeah.
And it's not just that, right? I mean, if you think about it, was that pixel chosen for the split across a number of, number of cities? And secondly, was it useful in doing the split?
Yeah.
So,
Oh,
sorry, go ahead.
yeah, sorry, just one more question was, if you go to the next slide where you're making the predictions.
Can you tell me, is it on the book or is
Yeah,
it
book,
on the
book, the next one.
next page? Okay.
Where you spoke about making the prediction, weighting, yeah, equations.
So it's hard voting by the looks of it. Majority of the weighted votes.
Right. So I was just wondering, like, why are we doing this thing of weighting? Like, so since we're doing this linearly training, right? You're training on the previous mistakes and you keep going. Doesn't it mean that the last one that you have trained on should be able to, in theory, do the best kind of classification? That should be kind of your best line, right?
Not really, because if you look at what's going on, every model is getting a weighted set of training samples based on the mistakes of the previous one. But that doesn't mean that. So what that means, two things. One, the model that's going to take this weighted sample has to focus on minimizing these mistakes. But in the process, it can make the mistakes that the previous model did not. And it may have its own inherent mistakes, so to speak, because of the reweighting.
Okay.
So as a result, if you just took the last one, I think that's where gradient boosting comes in, because essentially at the end, you just sum up all the sort of predictions because you're just minimizing the residuals. But in adder boosting, it makes sense because you are going to take for every sample, you're going to take what is the weighted prediction from this one, weighted prediction from this one, weighted prediction from this one, and then take a majority vote.
I see. Okay.
And that makes more sense because you have non-equally weighted all the training samples, and therefore it's not fair to just take the last one.
Yeah, the remaking of
so each successive model is stronger on certain examples and weaker on others. And so at the end, what you do is you average together all the models to get a better model, instead of just taking the last model, because as Sairam said, that model is strong on the specific data points that it emphasized, but it may not be strong on other data points that it didn't emphasize.
Right.
Yep.
Yep, makes sense.
I think it'll be cool to go through perhaps a mathematical example or graph example of how the updates and the learning gets done.
I think in this notebook that hasn't been given, but we can definitely try to track something down. I do apologize for not having like a code companion for this stuff. I really didn't have time this week.
I was thinking you could probably even see that by doing or applying what he calls the adder boost SAMME, and then just figuring out the probabilities for the classes that you're classifying in each, using the predict proba method to figure the probabilities for each of the classifiers you end up using as part of AdaBoost. That would tell you whether those predict powers are the same or different, or how different they are, because you're eventually averaging them rather than the voting, which he talks about.
So is that is specifically for regression versus the majority votes is for classification? That's what I understand.
No, not necessarily. I think what that says is if your models can predict class probabilities, then you can the scikit-learn implementation of AdaBoost uses the probabilities as opposed to the class labels, and therefore it performs better. So that's the hard voting versus soft voting idea that we discussed last week.
Further down in the book, in the next page. So you could, if you wanted to see what was being discussed, which is, will the classifiers, will the next classifier always perform better than the previous one? Then you could do that by applying this and looking at the probas.
Okay.
I think we're at time, so if there is nothing further to discuss or questions on this area,